Okay, so I just gave you a handout, and had there not been such a small class, I wouldn't have copied it for you because it's kind of a waste of paper, but it shows you what pictures of linearly dependent and linearly independent vectors look like. And so what you'll see is the red one on the page would be dependent vectors, and so dependent vectors lie in the same plane. And so an independent vector, they do not lie in the same plane. So you'll see that, and I consider a plane like a sheet of paper. So if you look at the red ones, if you drew those, all of those red ones would fit on one sheet of paper if you were thinking of it that way. But if you had a linearly dependent, it would be like, this is my sheet of paper, and here's a vector sticking out of it, in a different direction, like a different space. And so that I just wanted to show you what they look like. So that's what that one was. The other sheet that you have talks about a basis. And so that's what we're going to do today. It's handwritten, kind of lengthy, actually. But the good thing about it is that we won't have to write very much because it's all on there. So I did that to save us a little bit of time. Okay, you also, I'm going to give you back your homework 7 assignment. And there you go. All right, so let's go on with vectors. See if we can finish that up. A set of vectors in a vector space V is called a basis if S spans V and if S is linearly independent. Okay, so we have two characteristics there. In order to be a basis, it has to span and it has to be linearly independent. Okay, that's an excellent short answer question. Unfortunately, sometimes even though they're totally unrelated, my students, because they're on the same test, but my students sometimes miss this short answer question because they think I'm asking for subspace. So I want to backtrack a minute and talk about a subspace, just as far as definitions go. In order to be a subspace, first of all, it has to be non-empty. But the other characteristics are that, one, it has to be closed under addition. And closed under multiplication. Scalar. Now, so why are you talking about these at the same time? Because for some reason when we study, we say, oh, this one has two criteria and this one has two criteria. And then sometimes when you're putting those criteria on your paper, you sometimes put the closure properties under basis, and you put the spanning and independent under subspace, just because you get them mixed up. They're totally unrelated. So just remember, a subspace, this is what you're checking, but then the basis, that's when you're going to take the determinant and set it to 0 and see if it has solutions, that type of thing. So they're unrelated, but just because this one has two elements and this one has two elements, we get them backwards sometimes on the definition part. So keep that separate. All right, so let's take that off. You'll say, well, you're going to ask them together. I don't intend to ask them together. However, all your definitions are kind of together on the first part of your test. And so that's what we have to work around. Okay, so then if we keep reading down the handout I gave you, it says a basis must have enough vectors to span V, but not so many that it would be written as a linear combination. A vector space that has a finite number of vectors is called finite dimensional. And then we talk about the standard basis. The standard basis is the same thing as the standard spanning set. And remember, we talked about those in our last lecture earlier in this chapter. And so let's say it had 3 elements. Then you would have a 1 and 0, 0, and then a 0 and 1 and a 0, and a 0, 0, 1. Those are going to be your standard spanning sets or your standard bases. Now, we also talked about in a previous one that R3 would have 3 elements in its basis. P3 would have 4 elements because remember it's 3 plus 1, 4 elements in its basis, and M22 would have 4 elements in its basis. So we talked about those as well. Now it says example in your notes, we'll come back to that. It says if S equals V1 through Vn, this is really important. Not that part. That part's not really important, sorry. There's a really important part somewhere. It's all really important. There we go. It's on the back, I think. Okay, so it's just going through a little bit more definition stuff or theory stuff right now. So we're going to keep reading through there. It says if S equals V1, V2, V3, all the way to Vn is a vector space, then every vector in V can be written in one and only one way as a linear combination. So let's pretend for a minute that this 1, 2, 3, 0, 1, 2, negative 2, 0, 1 is a basis. So if it's a basis, that means that every single vector in R3 can be written as a combination. In other words, if Joseph picks 3 numbers, let's say Joseph picked 1, 2, and 3, there is going to be an A and a B and a C, but only one ABC combination that would satisfy it. Let's pick on Natalie for a second. Let's say Natalie picked 0071. Nice choice, Natalie. Right. So let's say that's what she picked. Then there's only one combination. There is a combination, first of all, for A and B and C that would satisfy it, but there's only one unique combination that would satisfy it. And that is what being able to be written as a linear combination is about. There's only one way to make that true. Now then, flip it to the back of that handout, or the second page of that handout. Here's the part that I thought was very useful, and you're going to use it a lot. It says if S equals V1 through Vn, and that is a basis for the vector space V, then every set containing more than n vectors is linearly dependent. Okay, so in that previous example that I wrote up, it says that 1, 2, 3, 0, 1, 2, negative 2, 0, 1 is a basis. So it has 3 elements. So that means that every R3 basis has to have 3 elements. If it has more than 3, it's dependent. So if you look below, it has that vector 1, 2, 1, 1, 1, 0, 2, 3, 0, 5, 9, negative 1. See how it has 1, 2, 3, 4 entries in it? I know that that is not a basis. Now, there's a question that on your homework for this week that says, how do we know that this is not a basis for R3 without a formal proof? Well, in order to be a basis for R3, it has to have 3 elements. So if I give you one with 4 elements, you know it's not a basis. If I give you one with 2 elements, you know it's not a basis. Because if it has a basis, they will have bases, right? But for every basis of R3, it has to have 3 elements. So you can kick some of them out really quick by using that dimension rule. Okay, so you've got one down there that says 3, 2, 1, 7, negative 1, 4 is not a basis. Then you've got another one, 1, 2, 3, 4, 5, that is not a basis for P3. So you can read through that one. And then you've got this one. Now, we're asking if this is a basis for M22, and we can't immediately just throw it out. What's the dimension of M22? 4, okay? And the way that we got that dimension was in a matrix. When you're finding the dimension, you're going to multiply those 2. So my dimension should be 4. Well, this one has 4. That doesn't mean it's a basis, though. But that also means it's the right number of sets, so we can't throw it out either. So if I give you one that does have the proper dimension, that's when you have to go through and check it. Now, a question was asked of me the other day, and they were like, you didn't give us one like this with matrices. And the reason I didn't is that it doesn't end up being a square, so you can't determine, you can't find the determinant of it since it's not square, and you have to solve it all the way out. So if I ask you one like this on a test, is it a basis or not? More than likely it's going to be the dimension part. I'm not going to ask you one that you have to work all the way out because you can't take the determinant of it. The dimension is called n, and then at the bottom of the page it shows you how to find the dimensions again. The dimension of Rn would just be n, so every basis would have n elements. The dimension of Pn is n plus 1, and the dimension of Mmn is Mn. All right, so somewhere on there it says there's an example done in class. So let's find that example done in class. I'm going to actually write up 2. Let's see. Okay, here's one. And here's the other one. So get those written and then we'll work them. Let's look at 40, 45, 49. All right, so here's our answers. Determine whether the set is a basis, justify your answer. This answer is no. Okay, flat out. No works needed. No, and the reason is a basis for R3 must have 3 elements. And this one doesn't. This one only has 2. And that's how we could say. Any questions with the first one?
Maybe this was not raise my hand because my question more has to do with the second one. Is there a possible scenario in which there's a set of 3 entries or 3 elements that is not called a basis?
Yes, that one's one. This one is going to be one.
So even though it's like supposed to be a basis, even though it's supposed to be like of dimension 3 of R3, it's not going to be the basis of.
Correct. Yep. All right, so looking at this first one, it had 2 elements. A basis has to have 3 elements, so we know automatically off the bat it is not a basis. Okay, and that's how you could justify it. Now, unlike this one, it had the wrong size, right? So we're saying, oh, well, this one has 3, so since it has 3, it must be. And the answer to that is no. Just because it has three items does not make it a basis. So what you have to do with this orange set on this side is you have to check the facts. Remember, to be a basis, you have to check these facts. 1, is it linearly independent?
Because like I had, J hat, and K hat, for example, they are linearly independent basis vectors in 3-dimensional space. So 1, 0, 0.
Yes.
1, 0,
Yes. Right, so when we're looking at determining, you can either start with, it doesn't matter if you start with span or start with independent, you're going to use both of them when this one, I know the answer to this one, the answer is no. Okay, so if the answer is no, it doesn't matter which one you start with. Either one is going to prove your point. But if the answer is yes, you have to do both of them. And my point with that is you don't know which one to start with. You can start with either one. Do you want to try independence? Or do you want to try spans first? It doesn't matter. You just have to start with one of them. So to check if something is independent, you're going to write the linear combination A times 1, 3, 0. Plus B times 4, 1, 2, plus C times -2, 5, -2. And for independence, we set this equal to the 0 vector. If we're using span first, we set it equal to the generic vector, U1, U2, U3. But this one, we're setting equal to the 0 vector because that's the definition of linearly independent or dependent. So coming up with our equation, we're going to have A plus 4B minus 2C equals 0, and 3A plus B plus 5C equals 0, and 0A plus 2B minus 2C equals 0. So my coefficient matrix would be 1, 3, 0, 4, 1, 2, -2, 5, -2. Okay, and then we're going to find the determinant. Now you're welcome to solve it all the way out, but you don't have to. I don't actually need to know what A and B, C, and C equal. I just need to know if they have, if there is a value, if there's a solution, and that's how we're going to use the determinant characteristic. Okay, so I'm going to use mine with the diagonal method. So I'm going to get -2, 0, -12. And I'm going to get going the other way. That looks like -24 plus 10. So in this first one, I'm going to get -14 minus -14. So I'm going to get 0. Did you get 0? What step? Nope. Not when you're doing the cross product. Cross product, you just copy your first 2 columns. You might use the cofactors. Do you use cofactors? Okay, so the way that you find the determinant is you recopy the first two lines because that's what makes your squares. So you start here and you go boom, 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 and then you go boom, boom. I didn't copy that down if you needed that.
Oh, that's what I was saying.
Yeah,
You didn't copy it down as a zero.
I didn't copy it down because it's 0. That's exactly right. So you got 0, right? Okay. So I got 0, and you're like, okay, great, I got 0, but I still haven't answered the question. I haven't proven it. I haven't justified it. I haven't done anything. I mean, I get points for that, but I haven't answered the question. And so the answer to this question is I get 0. So that means there is not a unique solution. There is a solution. It's infinitely many. There is not a unique solution. So it is dependent. Now that still wasn't my answer. That wasn't the initial question. That shows that it's not. That shows that it's dependent. It's not independent. But the question was whether it is a basis or not. So I still have to keep answering, keep justifying. And so the basis part is this. In order to be a basis, it has to be independent. So it is not a basis. Because it is not independent. Now, there were multiple answers for that one. Let's say instead of working it this way, you did spanning first. It's going to be the same determinant, so this one also would not span. And so you could have said this is not a unique solution, so this does not span, and since it does not span, it is not a basis. You could have also said this is not a basis because it's dependent. That would have been correct as well. The main reason that I picked this one, though, was that just because it has, and this was answering Joseph's question he asked initially, just because it has 3 elements doesn't mean it's a basis. It has the right number, but it still doesn't have the right criteria. So if you ever see one that has 3 elements, that's the one you have to check. If it has 2 elements, 4 elements, 62 elements, you don't have to check those. But if it has 3 elements, you have to check it. All right, so there's one more of those that I want to do. Make it where you can see it. There we go. And it's one of those that is the P2. I don't think I want P3. I wanted P2. All right, so let's go back. Let me go back. I was looking at the wrong numbers.
I'm not sure what spanning R3 exactly means, but I may have an idea. Is that supposed to mean that like the vectors are planarly dependent? They're not planarly independent potentially. So like this kind of scenario, rather than this one.
For spanning, as you can write, spanning would be, the spanning ones are going to be the same as the dependent, because they're going to have, you find them the same way, you find the determinant and go that way with it, but those are going to be the same pictures, yes, as those.
It's like if you did explain it in a class, I may not remember what you said the definition was. I was just trying to break apart what that phrase looked like it meant.
Okay, let me, my mind, I'm looking for this first, so if you'll give me just a second, I'm going to come back and I'll answer it. Or try my best to answer it, let's say it that way.
Yeah, I don't want to get too much of a tangent here in class.
Wanted one of those. I was about to work one that was a P3, and that was going to be way too big for our determinant, model, so I need to go back and work one that's a little smaller. There we go. Ooh. Seven minus 3 equals 4x squared. 6 plus 2. Okay, so we're going to work this one in just a second. All right, Joseph, I am ready for your question.
So with the spanning R3, could it be dealing with the situation maybe which, like two vectors, they're like linearly dependent or scalar multiples of each other, or like a situation in which the three entries are planarly dependent, they exist on the same plane?
Okay, spanning ones are not going to exist on the same plane. Spanning ones are going to look like that one.
So this would be spanning R3, this would not be a spanning R3.
Correct.
These would be like the XY plane, for example, and they wouldn't exist outside of it.
Correct. Yep. All right, so this one is in P2. So we wanted to do one of these because they're a little bit harder. I usually try to go with R3, but I wanted to, since we didn't have a good turnout last time, I wanted to do one that was a P3. Let me say it again. This is P2, and the reason that it's P2 is that it's all second-degree polynomials of degree 2 or less. Okay, so that's where this comes from. I know that the dimension of P2 is going to be 3. So the dimension of this is n plus 1. Here's my n right here. So 2 plus 1, which means this has dimension 3. So it looks really busy, right? But this is one element, and this is 2 elements, and this one has 3 elements. So in this particular case, I know I can't just automatically throw it out for wrong size, but that means I do have to check it. But now, let me put this on here for just a second. Let's say that I went further and I said this. Okay, so if I threw that one on there, that makes 4 elements, and this one would not be a basis because a basis for P2 would have 3 elements. This one has 4, so it's not. Okay, so that little size argument would work for P2 as well. Anything in P2 should have 3 elements. All right, so let's go back to the problem at hand. So this one does have 3 elements. That doesn't negate it or make it true either, so that means we have to check it. Okay, I prefer to start with checking the independence aspect of it because that's setting it equal to 0, the 0 vector, and so that's a little bit easier to explain. But since we just talked about spanning, let's do spanning this time. It doesn't matter where you start. So to see if something spans, I'm going to take A times this first vector plus B times this second vector, plus C times this third vector, now then, finally. And what we're going to do with that, starting that linear combination, what spanning means is that you can find any set in the plane, or it's not this one, sorry. We're not in a plane anymore. We're in polynomial space. So this would be ax squared, can't use a either, mx squared plus nx plus p. You'll say, what is this? This is the generic vector that is in P2. Any x squared polynomial. Now, I couldn't use a and b and c because I already used them in the problem. So that's why that didn't that had a change there. But that's the generic polynomial. So what happens in spanning is, whether it's P3, R3, M33, you're setting it up like the linear combination, but you're always setting it equal to the generic vector. And mx squared plus nx plus p would represent any possible second degree polynomial. Now, here's how our equations look. We're going to say 7a plus 6b plus c equals p. Now, so what I did there was of course we're going to multiply the a and b and c through, distribute them through, but that's all my constants. So 7a, 6b, c, and p are all the constants. So then I'm going to take all of my first degree polynomials. So negative 3ax plus 2bx minus 8cx would equal nx. So this is all the x terms. Negative 3ax plus 2bx minus 8cx equals nx. So then we'll do all the x squared terms. So we're going to say 4ax squared minus bx squared plus 5cx squared equals mx squared. Now let's rewrite it a little bit, make it a little bit more friendly. So this is going to be 7a plus 6b plus c equals p. Now, the way that you're looking or thinking about that second one with the x's, and we talked about this in our last class with a basic generic example. Basic example, not generic, sorry. Back in the day, you added basic polynomials that look like this, 5x plus 3x, and you know that that's an 8x. But what you were actually doing there is you took the 5 plus 3 and you worked those on the front and you just put it in front of an x. So this is the argument that we're using here as well. So if you look on the left side, you're going to get negative 3a plus 2b minus 8c all in front of x would equal nx. Yes, that's what I meant. So we get negative 3a plus 2b minus 8c equals n. And that's our second one. Now, the same thing would hold for the green one as well. We would have 4a minus b plus 5c equals m. Now, what we're solving for here, the x is all great and all, but what we're solving for here is the a and the b and the c. So you would have a coefficient matrix here, and your coefficient matrix would be 7, negative 3, 4, 6, 2, negative 1, 1, negative 8, 5. I'll double check my signs really fast. Those look great, and we're going to find the determinant of it. Y'all have some big numbers. What'd you get, Joseph? Negative 93. We're going to go, to save us some time, where I don't have to add all this stuff up, we're going to get negative 193. Is that what you said? No, you don't have to get up. Negative 93. I just didn't hear you. I'm sorry.
It's okay. No, I don't mind getting a check.
Okay, thank you. right, so multiplying it down, you would go, because I didn't put all my little marks on there, you'd multiply down this way, and this way, and then you backtrack and multiply down these, and you get all these big numbers, and hopefully, I trust the calculator for sure, that is what we get, okay? So what this shows in this little part right here is that it spans. It spans. Now, that doesn't tell me if it's a basis or not. It just shows me that it spans. And the way that I know that it spans is that the determinant is not 0. If the determinant is not 0, there is a unique solution. So A and B and C would have a unique solution. I don't know what it is, but it would have one. So that lets you know it spans. That doesn't help me, though. I have to keep going. So we have to do it again. We don't have to reinvent the whole wheel, but we have to do it again. So we have to say A times 7 negative 3x plus 4x cubed. I'm running out of room. Plus B times 6 plus 2x minus x squared. Plus C times 1 minus 8x plus 5x squared equals the zero matrix, the zero polynomial. Okay, so what we're doing with this orange one is we're checking to see if it's linearly independent. You have to do both pieces. Now, you don't have to write it all out because we know it's going to be the same matrix, but that's how you would set it up. So this one, of course, if you worked it out, you'd go back to the red and green steps over there. It'd look exactly the same as that, except you would have it equaling to 0. So we'd have 7a plus 6b plus c equals 0. And negative 3a plus 2b minus 8c equals 0. And 4a minus b plus 5c equals 0. You'd find that same determinant. It's the same one, same coefficient matrix, so it's the same determinant. This determinant is negative 93, which means that it is independent. So then you have to tie it all up. This is a basis because it spans and is linearly independent. Now let's talk about the orange part for a minute. That's a lot of work to prove something we've already done. So I'm not saying you have. I would like to see this somewhere in there to let me know that you knew what independent meant. But as long as you put it in there that it's equal to the zero vector, you can frame your proof the best way that you can. You can write out lots of it or you can write out small of it. Just make little small parts of it, but just make sure that you show me this part and that you address the independence issue for it. All right, so that finishes up this chapter, I believe. You have a homework set. Let me peep at your homework really fast. Got it? Got it. Remember, the standard basis looks exactly like the standard spanning set.
So the two conditions necessary to be a matrix, that's the two.
Mm-hmm. Okay, so it says, is this set a basis for R3? You're going to work the number 9. You're going to work it exactly like this, except it's not quite as hard because it's not the polynomials. You're going to work it exactly like this one. Now, you also have a practice sheet, a worksheet. It says worksheet 4, I believe. So between now and Monday, I would like for you to peep at worksheet 4 to see what questions you might have. And your test on this is going to be Wednesday.
I was wondering if it was going to be next week or the week after Thanksgiving break, which we have the test on. Like I was thinking it had to be practice.
Yes, it did have to be one of those 2 weeks, but I try to clear everything out off your calendar so that you can enjoy the holiday without any math.